Welcome to the physics revision video for section 12.9 for additional science or physics. What happens to radioactive substances when they decay? I've left out Rutherford alpha scattering from this, partly because it's higher tier only, and also because it needs quite a lot of detail, and so there's going to be a separate video for that, hopefully coming soon. There's some instructions for this to get the most out of it. Green boxed information is essential for foundation and for higher tier. Yellow box, higher tier only. Red box, if you're pushing up towards the A star end of things, that information's for you. There's lots of opportunities to pause the video and to test what you've just learned with some simple questions. I'd encourage you to do that because it's really going to help you retain the information. And finally, on that note as well, you shouldn't just be sitting here watching this passively. You should have a pad and a pen and be taking notes, and you're going to need it for the questions as well. So, first section then, the relative masses and relative electric charges of protons, neutrons and electrons. Well, there's a table, probably the best way to learn the information. You can see here the protons and neutrons found in the nucleus. Both of them have mass 1. The proton is charged with a charge of +1, and the neutron no charge, as the name would suggest, neutron for neutral. The electrons are not in the nucleus, they are around the outside of the atom. Much smaller mass than the protons and neutrons, almost 2,000 times less massive, and they have a charge of -1. So pause the video now for as long as you need to memorise that table. You can try look, cover, write, check if you want to, and then when we restart, I'll blank the values and you can check that you've learned it. Okay, so the values have gone now. Try and write the table out again and pause the video while you do that, and we'll check the answers afterwards. Okay, so just take a few seconds to check your answers against the table and we'll move on to the next section. Okay, so in an atom, the number of electrons is equal to the number of protons in the nucleus. The atom has no net electrical charge. So, you should be very familiar with this stuff from chemistry anyway, but let's have a look at it. There's a key up here to these diagrams, and these are the same key we're going to be using throughout the video. I won't always have it displayed because you're going to be familiar with it by the end. A blue circle with a plus sign is the proton, red circle with an N, a neutron, and the yellow dot with a little minus sign here is the electron. So let's build up our atom starting with the nucleus. In go the protons. This is just an example of an atom. 4 protons in this one. There are some neutrons as well, and that forms the nucleus, as we said. In the centre of the atom, very, very tiny compared to the atom itself. The atom is pretty small to start with. It's about 1/10 of a billionth of a metre. The nucleus even smaller than that. And on these diagrams that scale is not really shown. Most of the atom is empty space. So there go the electrons around the edge. Just a little note here that I've kept the electron shells you will have seen in chemistry. So that's the reason there are 2 separate circles here rather than having all 4 electrons together. That's just to avoid confusion with the chemistry, and I will keep that the same throughout the video wherever I show electrons. So, to show that our atom has no net electrical charge, what we do is we take the protons and we line them up next to the electrons, and sure enough, an equal number. So every positive charge is cancelled by a negative charge on the electron, and so there's no overall charge. Let's just check that you understand that. So some simple questions here. There are 6 diagrams and all you need to do is say yes, it is an atom, no overall charge, no, it's not an atom. If it has an unequal number of protons and electrons. So, pause the video while you do that, and we'll check the answers afterwards. Okay, so let's check the answers now, starting with A. Well, 1 proton, 1 electron, that's an atom. Simple. B, well, there's a slight trick here if you're not careful. There are 3 things in the nucleus and 3 electrons. But remember, all we care about is the protons and electrons, and there are only 2 protons and 3 electrons, an unequal number, so that is not an atom. For C, we have 3 protons and 4 electrons, so again, not an atom. For D, 4 protons and 4 electrons, so that one is an atom. E, 1 proton, 2 electrons, unequal number, not an atom. And for F, which looks kind of complicated because of all those neutrons in there, but it's still just counting, 4 protons, 4 electrons, sure enough, it's an atom. In fact, you've probably noticed that we don't really care about the neutrons. I can just remove them like that, and we don't need them to tell if we've got an atom. Just look at the protons and electrons. Okay, so that's neutral atoms. We're now going to look at what we can do with those atoms in terms of gaining and losing the electrons. So atoms may lose or gain electrons to form charged particles called ions. So we're going to see 2 examples here, the first of which is the formation of a positive ion. Now again, this should be very familiar from chemistry, but you do need to know it for physics as well, important to realise that. So here what we're going to do is those 2 electrons that just come up in boxes, we're going to remove them. You should know from chemistry again that the outer electrons are the ones that go first. So we do the same thing as we did last time. We take the protons from the nucleus, line them up with the electrons, and this time, because we've lost 2, there are only 2 pairs there to cancel each other out, and what we've got left over is 2 extra protons. So that means that because the protons are positive, the ion has a charge of 2+. Very important to realise that the protons are stuck in the nucleus and they can't be added or removed when we're forming an ion. It's always the electrons that are added or removed. Okay, so that's positive ion. Now we'll look at another example, a negative ion. Slightly more complicated nucleus, but the same principle applies. This time we're going to add an electron to that outer shell. There it goes. And we do the same thing. Line up the protons, line up the electrons, and this time we can see all those pairs disappear and 1 electron left over. So this atom has gained 1 electron and is now a negative ion. And we can see the negative charge go up there. We don't write -1. The number is only used if you have multiple charges gained or lost. Okay, so let's check you're happy with that. 6 more diagrams, and this time you need to say, is it a positive ion, is it a negative ion, or is it an atom? So it's summarising the last few slides. Pause the video while you do that, and answers in a second. Okay, so let's check through these. A, well, there's only a proton there, it's got to be positive, so it can't be an atom, and indeed it's a positive ion. It's lost the 1 electron it would have had to start with. For B, well, 2 protons, 3 electrons, meaning we've got 1 extra electron, and so we've got a negative ion. For C, 3 protons, 3 electrons, so you remember that means no overall charge, we've got an atom. For D, 4 protons, 3 electrons, an extra proton means positive ion. For E, well, that's an atom again. 2 neutrons there, but we don't care about those for telling if you've got an ion or an atom. So 1 proton, 1 electron. And again, F looks more complicated, but it's still just counting 4 protons, 5 electrons, so we've got a negative ion. Same thing here applies as for atoms. We can get rid of the neutrons completely and it doesn't matter. If we're trying to see if we've got an ion or an atom, all we care about is protons and electrons. Okay, moving on now, we're going to focus a little bit more on what's going on in the nucleus, and in particular how it relates to different elements. So, atoms of different elements have different numbers of protons. The total number of protons in an atom has a special name called the atomic or sometimes proton number, and every single atom of a particular element has the same number of protons. So here's some examples. Simplest atom there is, hydrogen, 1 proton, 1 electron. Atomic number of 1 because of that proton. Helium, next atom in the periodic table. 2 neutrons here, but no effect on the atomic number. It's just the 2 protons that mean it's got an atomic number of 2. And finally, carbon, 6 protons in the nucleus, so an atomic number of 6. Very important to realise, every hydrogen atom, 1 proton. Every helium atom, 2 protons. Every single carbon atom, 6 protons. So if you see something with 6 protons, it's always going to be carbon, no matter what else has happened. Okay. Now, there's another quantity you need to know about, this time called the mass number. And this is the total number of protons and neutrons in the nucleus. Okay, at this point I'm going to lose the electrons because we're going to be focused mainly on the nucleus. This is where all the radioactivity happens, if you like. So we're going to lose the electrons. If we're not worried about ions, that's not a problem, because the only place where electrons are important is in the formation of ions. Okay, so we're just going to look at the nucleus, the carbon atom we looked at before. And what I've done is I've lined up all the neutrons and protons, 6 of each in this case, giving us 12 in total. So that gives us a mass number of 12. And what you can see down here is the letter C, which is the chemical symbol for carbon, and the mass number goes before it and at the top. Okay. The atomic number that we mentioned before, which is the number of protons, there they go, goes at the bottom, and that's 6 for carbon, like we said. Now, because as we said, all carbon atoms have got 6 protons, sometimes that number there, the atomic number, is not given. And that's because the C is enough to tell us 6 protons, because of every carbon has 6 protons. Okay. There is another way to write this, which you'll need to know as well. So what we do is we take the C over there and give it the full name, carbon, and then because the carbon is enough to give us the 6 protons for the atomic number, all we need to do is stick the mass number after the name of the element. So that would read carbon 12. So our carbon 12 atom has 6 protons and 6 neutrons. Okay, so let's check whether you're happy with that. Look at the diagrams of the nucleus. Again, the electrons have gone now. And see if you can write down the name of the element using that technique we've just shown for both the types of name. Okay, so pause while you do that, and we'll check in a second. Okay, so first one, A, hydrogen, 1 proton, no neutrons, so the mass number at the top here is 1, and the atomic number or proton number is 1 as well, and so we'd write that as hydrogen 1. Second example, the helium, 2 protons and 2 neutrons, so add those two together to give us the mass number of 4, and the number of protons goes at the bottom, 2, 4, 2, He, or helium 4. And finally, this nitrogen example over here, Well, if you count carefully, we've got 1, 2, 3, 4, 5, 6, 7 protons, which makes it nitrogen. And in this case, 1, 2, 3, 4, 5, 6, 7, 8 neutrons. So add those together to get our mass number of 15, and the 7 protons go down there into the atomic number. So that's nitrogen 15. Okay, so that's what makes a particular atom belong to a particular element. Now we're going to look at some different versions of those atoms for a particular element, and that gives us something called isotopes. So atoms of the same element which have different numbers of neutrons are called isotopes. So let's look at an example of this. This is just using the same ideas as we had before. This happens to be an atom of an element called beryllium, which has 4 protons and 5 neutrons. So it makes 9,4Be, or beryllium-9. But there are other examples of beryllium atoms. Okay, all of them have got 4 protons. They have to, remember, but you can have different numbers of neutrons. So these other 2 diagrams here are pictures of the nucleus of 2 other isotopes of beryllium. So see just now if you can write down what those isotopes of beryllium are in the notation. Restart the video after you've paused and we'll check. Okay, so first one, 4 protons, 7 neutrons, so that one is beryllium 11. And the third one, 4 protons, 3 neutrons, that one is beryllium 7. So there are 3 examples of isotopes of beryllium. Now, pretty much all elements have several different isotopes, and some elements have got a lot of different isotopes that you can find. Okay. So, what do these isotopes do? Well, the key thing is that some isotopes are stable. That beryllium-9 isotope we looked at is stable. It doesn't undergo radioactive decay, and it tends to be that the stable isotope is the most common one, and that's mainly because it hasn't decayed away since it was created. And pretty much all the material on Earth was created in a supernova explosion by a previous star, and then the highly radioactive isotopes will have decayed away gradually, some of them quite quickly, depending on half-life, which you should remember from year 10, and the stable ones remain. Now, some of the unstable ones will still be here because their half-lives are too long to have completely decayed away. But the key point is that there are lots of unstable isotopes which are radioactive. So both beryllium-11 and beryllium-7 are unstable, and therefore they give out radiation. Okay, and we're going to look at the details of that now. For those of you looking at the higher grades, the reason for this stability issue is the number of neutrons. There's a kind of golden ratio, if you like, of the correct number of neutrons to make a nucleus stable. Down the bottom end of the periodic table, in the low atomic numbers, it's about 1-to-1 ratio. So you remember carbon-12 had 6 protons and 6 neutrons, an equal number. This beryllium atom here, not quite, but nearly, and you can see that where there's a big difference between the number of protons and neutrons, it becomes unstable. When you get up to higher atomic numbers, as you'll see later on, the stable isotopes tend to have a slightly larger number of neutrons, so that proportion shifts to be slightly more neutrons than protons. Okay, so what we need to know about is how these nuclei decay. And there are 2 main things that you need to know, and that's alpha and beta decay. They are not the only ways for the nucleus to decay, but they are the 2 that you need to know about. So, first of all, just a reminder of year 10 stuff. What is an alpha particle? Well, an alpha particle is the same as a helium nucleus. It's 2 protons and 2 neutrons. It has this symbol, which is Greek letter alpha, and if you think about it, it's got 4 particles in total in the nucleus here, so a mass of 4, and because of the 2 protons, its charge is +2. And so we put a 4 in the mass number and a 2 in the proton number. The other type of radioactivity you need to know about is beta decay. Now, beta particles are just electrons, okay? And they have the Greek letter beta as their symbol. And if you remember, their mass is not quite, but nearly 0. It's a very tiny fraction, about 2,000 times less than a proton. And so we can say 0. And its charge is -1. Now, there's a little bit of a stretch here in terms of how this works with the notation, because what I said to you before was that the top number here is the mass number, so total numbers of protons and neutrons, and the bottom number here is the proton or atomic number, so total number of protons. But in fact, when we're talking about radioactive decay, we kind of use them in slightly different way in this idea of mass and charge. So what actually happens is we write a 0 and a -1 before the beta particle. Now clearly you can't have -1 proton, so that -1 is representing the charge of the electron now, and that's going to be very important later on. Just as a little additional bit of information, you may remember from year 10, the other type of radioactivity is gamma, and gamma rays are not particles really, they are photons, high energy photons, high energy electromagnetic radiation, symbol gamma. They really do have 0 mass and 0 charge, so gamma rays are written with a 0 before the gamma symbol. Okay, so that's the basic information about what alpha and beta are, and now we kind of need to use that. So, let's look at alpha first. What actually happens in a nucleus during an alpha decay? So, here's a nucleus. This is boron 11. Just a note, by the way, about how you know if you have a particular atomic number. How do I know that 5 is boron? Well, you can look it up on the periodic table. If you want to pause the video and get your planner out now with the periodic table in it, you could do that. That might be quite useful if you're interested. You don't need to be able to do this for physics, but it's good to have a familiarity with it anyway. So how does this work? Well, if you remember, the periodic table is arranged in order of atomic number. So starting in the top left-hand corner, there's 1, 2, 3, 4, 5. So for our particular nucleus here, we're interested in atomic number 5, which is down here. And if you look on the periodic table, we'll fill those in with the element symbols. It's hydrogen, helium, lithium, beryllium, and number 5 is boron. So it's literally just looking up the atomic number on the periodic table in that way, and it keeps going. It would go 6, 7, 8, and so on, all the way across the rows. Okay, so there's our boron nucleus, and if you remember, alpha decay, an alpha particle over here is 2 protons and 2 neutrons. So what I've just done is I've the boron nucleus decayed, and I've moved the 2 things we got out over to this side. So this is what's left of the boron nucleus, and this is the alpha particle that's come out. And I've just put the original boron nucleus back over here so we can see what we started with and what we've ended up with. And we write these decays a bit like a chemical equation, with whatever you started with on the left hand side, an arrow, and then what you end up with. And if there's multiple things, you just put plus sign in between them. So what have we got? Well, we know we've got the alpha particle because we're talking about alpha decay. And the question is, what's this? Well, you just use the same rules as we did before, and this turns out to be lithium. Now, you won't be required to know to look up that it's lithium in physics. all you'll be required to know is what are these numbers here. So clearly this is 3 protons and a mass number of 7, because we have 1, 2, 3, 4, 5, 6, 7 neutrons and protons in total. Well, it's fairly easy to see that if you've got the pictures to count, but there is an easy way to see it as well just by looking at the numbers. And again, it's a bit like in chemistry when you're kind of balancing equations, you've got to make sure that things match up properly on both sides. Now here, we're not talking about matching up numbers of atoms. Here we're talking about matching up, first of all, mass. So the total number of protons and neutrons has to stay the same on both sides. So the 11 over here is made up of the 7 plus the 4. And then the second thing we're looking at is conserving charge. We can't create or destroy charge. So the 5, the 3 and the 2 have to match up as well. So that's the rule. And in fact, that rule applies for alpha decay, beta decay, any other type of decay that you like. That rule applies. This is just being used for alpha decay here. Okay, so that's our example of alpha decay. So what you need to do now is, here are some more of those equations, all of them alpha decay. You need to fill in the gaps where the little underlines are. Pause the video while you do that and we'll check your answers in a second. Okay, so starting with the top one, well, there's the missing numbers. We've lost 4 from the top of this uranium atom here to make something called thorium. Again, you don't need to be able to tell that it's thorium, you just need to be able to go 238 to 234 on the top, 92 to 90 on the bottom. And all the rest are the same, the difference is 4 at the top and 2 at the bottom. So 204, 82. C and D are a little bit different because you've been given the products and asked for what we started with. So you have to add 4 and add 2 to the isotope on this side, giving us 222 and 88 for C and 232 and 90 for part D. Okay, so it really is just that difference of 4 in the mass number and difference of 2 in the proton number. Okay, so that's alpha decay. Beta decay is slightly more complicated. It's not just simply an alpha particle being spat out of the nucleus. So we need to look a little bit more carefully. So here's a nucleus of carbon-14. And what happens is, we're just going to highlight this neutron here, because what happens in beta decay is that neutron turns into a proton and it spits out an electron in the process. Okay, so there it goes. The electron flies off as a beta particle and we're left with a nucleus that has changed one neutron into a proton. Okay, so same as before, I'm just going to move that decayed nucleus over to this side and replace the original one so we can set up our equation. So there you can see there's the proton that's changed, there's the neutron in the original nucleus. Sticking our arrows and our plus signs, there's our beta particle, if you remember, no mass number, well, 0 mass number, and -1 because it's negatively charged. And if you look here, this time we have 1, 2, 3, 4, 5, 6, 7 protons. So that's going to give us nitrogen if you looked in the periodic table. And if you look, the mass number has not changed. And that's because all we've done is switch a proton for a neutron, so the total number of protons and neutrons combined is the same. But what has changed, you can see, is at the bottom here, the atomic number has gone up by 1 because of this -1 in the beta. So we've got 7 minus 1 gives us back our original 6. So we're still doing the same thing. Mass is conserved very straightforwardly because the beta particle has a 0 mass number. And charge is conserved. You'll be a little bit careful here because you've got to remember that adding a minus is the same as subtracting. So 6 equals 7 minus 1. But other than that, it's exactly the same in terms of the conservation as the alpha decay. Okay, so let's just check you're happy with that. 4 more to do, similar to the alpha particle decay. Pause the video, make sure you can fill in the gaps. Okay, so let's check your answers. Well, for part A, we've got 60 and 28. That mass number at the top unchanged. Proton number goes up by 1. Same thing for the second one. Mass number unchanged. Proton number up by 1. For part C, well, again, slightly different because we're trying to find the thing we started with. So we've got our mass number of 1 here goes up to give us 2. And 2 minus 1 gives us back our original 1. Mass number unchanged still. And for D, well, there's the answers. Same rules as before. Okay, so that's separate alpha and beta. It's relatively straightforward to see that when you know which one you're looking for. So we're just going to mix it up a little bit now. This is probably more or higher tier. But still, I think foundation tier people could have a go at this. So pause the video, and this is a mixture of alpha and beta decay. And in the last 4 questions, I'm looking for which type of decay we've got, rather than what the mass number and atomic number are. So pause, and then we'll check. Okay, so let's go through. Well, alpha decay here, so we're going to lose 4 from the top and 2 from the bottom. 4 from the mass number, 2 from the proton number. For part B, beta decay, mass number unchanged, proton number up by 1. C, beta decay again, same thing. D, alpha decay, lose 4 from the mass number, lose 2 from the proton number. Okay, so now we're doing it backwards for these last 4. We have to look at what's happened. Well, we've made a mistake because that's not right, is it? That should be 225. Sorry. And that would be alpha decay if I'd got that correct. This one here, beta decay, because we have a mass number change of 0 and the proton number goes up by 1. And down the bottom here, part G, alpha decay, and part H, beta. So there you go. Right, last thing then, which is kind of a little bit separate from what we talked about, and it's a lot less technical. You just need to kind of remember a few key points. And it's sources of background radiation. Where does background radiation come from? You should remember from year 10 that background radiation is kind of everywhere. And these are the main sources. Radon gas, it does depend on country. Some countries have more radon gas than others. And this is why I haven't put precise percentages on here, because you don't need to remember them. You just need to know roughly. So radon gas is a big source of background radiation. And then food and drink, something called cosmic rays, which we'll discuss in a second, and rocks are the other major sources out of ones that we call natural sources of background radiation. So they are there and would be there even without man. Now, you might say, well, food and drink wouldn't necessarily be there without the human race. But the important thing is that anything chemical we do to a radioactive isotope won't make any difference. So all we've done when we're making food and drink is chemical reactions, not nuclear ones. So the stuff that went into the food and drink would still have been radioactive anyway, and so it would still contribute to the background radiation. Now, if you look at that, the important thing to realise is that natural sources of background, which are these 4 slices here, make up the vast majority of background radiation. And there are really only kind of 2 major sources of artificial background, medical and nuclear and industrial. And the key thing to realise here is it's a common misconception. People think that nuclear testing and the nuclear industry in terms of power stations and other things like that is the major source of artificial or man-made background. It's not true. The medical uses of radioactive materials and of X-rays give us by far the biggest contribution to artificial background. So medical is the most important one. You might say, well, why are we increasing our background radiation level using medicine? Surely that's dangerous. Well, yes, there is an increased risk, but you've got to realise that risk is massively offset by the benefits of these medical procedures, both in terms of finding out why people are ill and in treating them. So if we didn't use it, there'd be far more deaths as a result of lots of different diseases, and this slight increased risk, and the main increased risk is of cancers, is acceptable. You have to realise that this total amount of background radiation is incredibly tiny. It's measured in something called millisieverts, and the average annual background in the UK is about 2.6 millisieverts, which is tiny. And that means that there's an incredibly small risk from this background radiation, therefore an even smaller risk from medical background. Now, this is not to say that nuclear industry is not dangerous in any way at all. Whilst the total background contribution is very small, obviously in incidents like the Chernobyl disaster, locally, and in fact over quite a wide area in that case, for a relatively short amount of time in terms of the total history of the Earth, there was a significant contamination from nuclear fallout. But still, that's a tiny, tiny amount of the total background we receive every day. Okay, that's pretty much what you need to know. That's the end of this video. Thank you for watching.